Hi again. Now that you have the terminology and the goals of why we're doing this, hopefully embedded in your thoughts, we're going to actually go through some of these images and the tutorial. So we're going to choose this first tutorial and we're going to think about what's happening with dissolution. In each one of these images, what you're seeing is a close-up image of the thin section picture. It's telling you here that we are in plain polarized light. Many of you will know what that means. In some cases, we'll be looking at cross-polarized light images, and in some cases, we'll be able to toggle between a PPL image and an XPL image. Notice also that what we're looking at here is the scale. 50 microns across is the amount that we're going to be able to see. And then finally, it's going to tell us what image we're on. You'll notice that I will be moving the cursor around the image like this, and as long as it stays an arrow, that means I cannot click and receive new information. And so even though I'm not able to click on this blue stuff, hopefully you will remember that this is the artificially colored epoxy that is showing us the primary porosity of this aqueous. So this would represent what is left after the sediment comes in and is deposited, and that there's some amount of compaction that has already happened. Now, for each of these images, not only did they take the image with a standard petrographic microscope, they then spent hours and hours using an electron microscope to analyze each grain and verify what it was that that grain is specifically. Now, in this case, they may or may not have used the electron microscope, but what I'd like to point out to you is that even though this grain has a pretty clear, similar color in PPL, and so does this grain, notice how some of these grains are really rounded and pretty clear in the middle. Oftentimes that's going to turn out to be quartz. Hopefully you guessed quartz. But in this case, if you are unfamiliar with what is meant by cleavage, here you go. There could not be a better example of mineral cleavage. Look at how you have all of these cracks in this crystal, but they show up as parallel to each other. So we have cracks that are nearly vertically oriented, and then we have cracks that are nearly horizontally oriented and parallel to each other. So we have the indication of one cleavage set in this orientation and a second cleavage set in this orientation. So we're looking at a relatively low relief mineral, 2 cleavages, it's in an aqueous. Notice that that cleavage even gives us a really nice stair-step pattern around the edge of the crystal, which in some cases is relatively blocky in its outline. So hopefully you've already guessed that this is a feldspar. There's actually a third cleavage that is not easy to pick out. But what we're going to be focusing in on in this image are these oddly colored pale green. We're getting some diffraction of light, changing our wavelength of light here. So we're getting a diffraction in this space along the cleavage, and we're going to be looking at these brownish areas. So notice that I sort of inadvertently clicked on this, and now we're getting the information of the interactive tutorial. So remember, we learned that term vacuole or vacuolization. Here we go. This is the vacuolization of this feldspar. And we're learning about minor dissolution along cleavages. Next image. Take a look. Again, I can move my cursor around, but I've already explored this tutorial multiple times, and so I know this is the main point. Recall that perthite is a kind of feldspar where we have intergrowths of K-spar and albite, potassium-rich K-spar and sodium-rich albite. All right, there's a lot to look at here, so I'm going to zoom around. Here's our first bit of information about this. This is a volcanic rock fragment. It may be difficult for us to tell, especially because it's altered, okay? But it did highlight, there's the grain of the fragment, and we have multiple mineral patches in that fragment. Let's see what this is. Another volcanic rock fragment. So this might almost be getting over into a litharenite where we have volcanic rock fragments. Let's see what's up here. Another volcanic rock fragment. Okay, so this would be what we would call a very immature sandstone. Let's take a look here. Plagioclase. This is where they would have used the electron microscope to confirm this. This is a plagioclase. This plagioclase is pretty intact. We have a little bit of dissolution here and maybe a little bit here, but we're contrasting that with what's in the center of the diagram. There we go. This is a plagioclase, but what's intriguing about this plagioclase is it has secondary porosity that's indicated by the blue epoxy. There it is. All right, next image. Here we go. Again, I've looked at most of this. All right, we're clearly going to be looking at what's in the center, so let's do that first. Notice how blocky this grain's outline is. Not surprisingly, it's detrital plagioclase. Hasn't been carried very far because it's not rounded. The other thing is, as it breaks, it just tends to break along those cleavage planes. Do you remember what this is going to be called? You guessed it, there it is, our secondary porosity. As much as possible, I'm going to pause so that you have to actively try to recall what the term is, because that effort of active recall on your part is what puts the information into your short-term and longer-term memory. And remember, I'm going through many of these images to really hope, in the hopes that the repetition is going to help you out with a longer-term memory. Okay, well, we hadn't looked at what was the information available to us here in this odd little area. Okay, we've got a calcite cement here. Okay, so we have our arkose. Our arkose has some grains that look like perhaps quartz or feldspar, looking very much like quartz here. We have our blocky feldspar grain, and then into that primary pore space, a calcite cement deposited and grew from the initial groundwater. We don't know whether the groundwater then changed composition that made it more likely for this to be dissolved. Possibly these areas that are dissolved were contributing calcium so that the calcite could form. These are the kinds of interpretations for our balanced chemical reactions. These are the interpretations that we'll need to make. on a future slide. All right, lots to look at here. Let's dive in. Not surprisingly, hopefully to you, because of its rather clear nature and somewhat rounded shape, you do see little bubbles inside quartz, and that's very often because when that quartz was forming, whether it was in a hydrothermal system or in an igneous or metamorphic rock, quartz can also trap little bits of fluid or gas, but these are not associated with the diagenesis if they're in the heart of this quartz grain. Okay, let me make sure we see where that's happening. Quartz cement, we're getting quartz cement filling the primary pore. There it is. Now, the quartz cement is filling the primary pore, but I want you to notice something. See how this patch cuts across here, and let me get rid of that if I can. Here, it looks very much like this bit of quartz cement is filling in between grains, but you'll hopefully recall that this area is actually thought to be a quartz cement as well, but we have the grain, the original grain boundary highlighted here because there are little bits of clay along the edge of that initial grain boundary. Think about this, we have these quartz grains tumbling around with shale, or we might have wind-blown dust come in later. So this is telling us, hey, there's your original quartz grain, but that quartz grain is dissolving and reprecipitating right here, and so the grain itself is recrystallizing and contributing to the calcite, or sorry, to the quartz cement. This can in part be due to the compaction putting a lot of pressure or work. Remember, we'd be thinking about this thermodynamically. As this grain is mashing into this grain, we're having a lot of work done, high pressure right here, and that can contribute to the reprecipitation. All right. Another detrital quartz grain, but notice we've got a funny boundary across here. Oh, now it's telling us about detrital. Sorry about that. Okay, let's come into this blue area and see what's going on. That's the remains of the feldspar that at one time filled in this entire area that has the heavy outline. And of course, what's this blue stuff then? Secondary porosity. Detrital quartz, take a look. Take a look at that. Why did they draw the boundary of that detrital quartz there? What does that mean about this? Ha, quartz cement. Here's that straight edge they're talking about, and what is this? It's a really large secondary pore that at one point was an entire grain, maybe a feldspar grain, based on how sharp the boundary is. There it is. It's a skeletal grain. There's hardly anything left. Okay, This slide asks you to think about where is the aluminum going? Where is the silicon going? And that's exactly what we're going to be thinking about as we look at our solubility diagrams later. Notice here we've got this view is at 200 microns across the lower side of the slide. So actually I'm not sure if it's the box itself represents the length 200 microns. That makes more sense to me. Whereas in the past, some of those images were blown up to 50 microns. So we've zoomed out, we're looking around at this. Let's see what we find. Okay, it is impossible to tell case bar and albite or intermediate plagioclase apart in thin section. With a thin section, they have exactly the same characteristics of cleavage and the same optical characteristics. And so very often, if it matters to you to know what kind of feldspar is there, prior to the widespread use of electron microscopes, people would use a stain. They'd actually cut their rock and then let it sit overnight in a dye, and that dye would preferentially adhere to the type of feldspar that you're looking for. So this is a case bar, this is a case bar, so is this, so is this, so is this, okay? And they would have either used a vacuum to soak that cut surface with the blue epoxy first. That's one option. Or they might have cut this, put it in the dye, and then later put in the blue epoxy. I'm not sure which. Look at this. This is quite curious that we see the outline of a grain even as we notice that the blue epoxy is filling it. This is called a Bolduc Pour. Sounds like something you'd find in a damp bathroom or a gardening shed. The Bolduc Pour. Lots of primary intragranular porosity, but take a look at this. It's another Bolduc Pour. We have a little bit of the feldspar left. Oops, I got excited there. Okay. Let's take a look. Again, we've zoomed in. We're mainly being directed to look toward the yellow stuff. If we're thinking about what we learned about dyes, we might be anticipating that this is Untitled Chapter with that yellow stain. And notice there's not as much cleavage to work with, but there is some cleavage to work with. And you can see how it is angular in some places and has broken. Okay, this used to be a case bar that I'm outlining with the cursor. Why did this grain dissolve while the grain adjacent to it did not? There you go. We can make some guesstimates or inferences, but this is basically what we have to work with. Another Bolduc Pour. See how it mimics a Plagioclase lath. And here's another sandstone. Lots of quartz throughout here. Lots of quartz. This pour is larger than we might otherwise expect. Let's make sure we read all that. Okay, so this rock initially would have been an arkose or a subarkose because it had some feldspar and a lot of quartz, but now because of diagenesis it has far more quartz rather than feldspar, so they call it a quartz arenite. I think that detail is really important when you're trying to think about how did this sandstone layer form. I think it's less important that subarkose versus diagenetic quartzite. That's less important unless you're trying to understand the reservoir of that is holding the groundwater, or the reservoir that's holding your hydrocarbon. Okay, that is the end of the tutorial that is mainly focused on dissolution. I don't want to overload you here. I know that when I'm going through this, it's a slower process than when you would be going through it yourself. You might be able to click through more rapidly. So I'd encourage you to take a break now, because I will be recording 2 more tutorials, one that will be focused more on feldspars, and the last tutorial which will be focused more on